Hello everybody, in this lecture we will be solving 1999 IMO problem number 4. Here is a view of this problem. We would like to find out all pairs of positive integers n and p such that the three following conditions are satisfied, namely p is a prime, n is less than or equal to 2p, and finally n to the power p minus 1 divides p minus 1 raised to power n plus 1. So given these three conditions, so find all pairs np of positive integers. Okay, so let's assume that np is a pair of positive integers that satisfy these three conditions. We have the following simple case work. So let's consider what happens if n is equal to 1. If n is equal to 1, then 1 to the power p minus 1 should divide p minus 1 raised to the first power plus 1, but that's simply equal to p, so 1 would obviously divide all the prime numbers. As a result, one of the solutions will look like 1p for any prime p. So that's one solution. Secondly, so therefore for the sequel we can consider just the case where n is strictly greater than 1. And now let's start with the prime p. P is equal to 2, I should say. When p is equal to 2, then this condition becomes n raised to the power 2 minus 1, which is simply n, must really divide 2 minus 1 raised to the n power plus 1, which is simply equal to 2. So therefore n should divide 2, but so this would imply n also being strictly greater than 1, n must be equal to 2. As a result, we have our second solution, namely 2, 2 also satisfies the three conditions. And the second condition is obviously satisfied as well. So therefore, for the rest of the proof, I will simply assume that not only n is strictly greater than 1, but I will also assume that p is an odd prime greater than 2. So these are, for the rest of the discussion, I will assume that the n and p have satisfied the following conditions. Let me remind you of the given condition, the third condition of the problem again. And now I claim that, check this out, n is greater than 1 and p is odd, so p here is odd. So therefore p minus 1 would be even, raised to any power is still even, plus an odd number, the whole thing would be odd. So therefore n itself must be odd as well. So therefore n is odd as well. So p is odd, but n is also odd. So that's an additional restriction that I need to be careful about. So n being an odd number, let's consider the following situation, or a type of an extremal argument here. So let's say that m plus 1 is the least prime divisor, and we've done it multiple times, least prime divisor in previous videos of n. So let's assume for a moment that m plus 1 is the least prime divisor of n. N is an odd number, meaning m plus 1 is odd. So therefore m itself is even. M is even. M is an even number. Now, because n raised to a certain power, p being strictly greater than 2, n raised to a power more than 1 divides this expression, it means that n itself should divide it, but n is itself divided by m plus 1, suggesting that m plus 1 should also divide this expression as well. So therefore m plus 1 divides p minus 1 raised to the nth power plus 1. In modular arithmetic language, that's simply p minus 1 to the n power plus 1 being congruent to 0 in mod m plus 1. Or you can simply move that plus 1 to the right hand side and write it as minus 1 if you will. Yeah, let me just do it that way actually. Raised to the nth power is congruent to minus 1. We know that because m plus 1 divides n, and yet m plus 1 also divides this expression here, so therefore m plus 1 cannot divide this expression, or if you will, it can definitely not divide p minus 1. So therefore, so this implies that m plus 1 divides not p minus 1. So therefore, this would imply that if I apply Fermat's-Little theorem, p minus 1 raised to the mth power is p minus 1 being relatively prime to m plus 1. P minus 1 raised to the mth power is congruent to 1 in mod m plus 1 by Fermat-Little theorem. Now again, so n is m plus 1 divides n, so therefore m itself is, m being a number less than m plus 1, is definitely relatively prime to n, because m plus 1 is the least prime divisor of n. So as a result, so we already know m and n have a greatest common divisor of 1. By Bézout's theorem, or Bézout's result, we know that there exist positive integers x and y such that an x minus my is equal to 1 by Bézout. And therefore we can easily write the following. So p minus 1 raised to the nth power is simply equal to p minus 1 raised to, if you move my plus first power. But then I can play things around. So p minus 1 raised to the mth raised to the yth power times p minus 1 raised to the first power. So we know that m itself is even. Let me write that down here. So this m here is even, making the product even, and so therefore nx must be odd, right? But n itself is odd, so we have established it early on. So because n itself is odd, this would imply that also x itself must be odd. Sorry, x itself is odd. Now I will consider this expression here. I will take the mod m plus 1 of both sides of this expression. So for the left hand side, so we have already established two important results, namely this one and this one. So therefore, if I take the mod of the left hand side, so I can write it in so p minus 1 raised to the n raised to the x power, so I can just put a bracket here. So p minus 1 raised to the nth power in mod m plus 1 is simply equal to minus 1, so it would give us minus 1 raised to the x power. And recall that x is an odd number, so therefore this is simply equal to minus 1. So minus 1 is congruent to, on the right hand side, so we already know that p minus 1 raised to the mth power is equal to 1 raised to the yth power times p minus 1, like that, which is simply p minus 1. But then in mod m plus 1, so but then when you compare these two, the minus 1s would cancel out, which would imply that p in fact is congruent to 0 in mod m plus 1. What that means is that we are dividing a prime by another prime and the remainder is 0. So therefore this implies, so it can't be, right? So a prime cannot be a positive multiple of another prime unless they are equal to each other. So p is actually equal to m plus 1. And recall that m plus 1 is the least prime divisor of n. So therefore, now we can go ahead, well, yeah, and m plus 1 divides n. So therefore, p itself divides n. But now for the first time I will consider this condition now. So when you combine this result with the fact that n is less than or equal to 2p, combining these two, what does that mean? It means that, for instance, from the first one we recognize that n is equal to simply something like kp, where k is a positive integer. So therefore there's only one integer that can be satisfied by, also knowing that n is odd, right? So k cannot be 2. So the only k that would work, also combining it with this result, is k equals 1. So therefore n is actually equal to p. Now we can go back to the original problem and look at the condition now carefully. So we have the condition n to the power p minus 1 divides p minus 1 raised to the n power plus 1 now has transformed into p raised to the power p minus 1 divides p minus 1 raised to the power p plus 1. And now I can make use of the binomial theorem to expand this expression and see how many p's that this expression would hold. So therefore this expression here, p minus 1 raised to the p power plus 1, is simply equal to the summation. Let me just write the plus 1 in the front. J equals from 0 to p, p choose j, p to the power p minus j, that's a minus sign here, times minus 1 to the power j. And now I will further split it, 1 plus, in fact I will just write it from j equals 0 to p, p choose j, p to the power p minus j. Again, so let's keep this one intact, except that I will stop at p minus 2. So I will plug in p minus 1 and p separately. If I plug in p minus 1, that would give me p choose p minus 1, p raised to the power p minus 1, minus 1 to the power p minus 1, plus finally p choose p, p to the power p minus 1 raised to the power p. So the 1 plus the summation sign would remain, minus 1 to the power j, j equals from 0 to p minus 2. Okay, so how about this guy here? So this is p choose 1, which is just p, times, so this guy here, p is an odd prime, so the power is even, so therefore this guy here is just 1. And now here this one is p minus p, so they vanishes, so you have a plus 1, so there's another p here. So p times p plus, so this one is a 1, p raised to the 0th power is 1, and then minus 1 raised to an odd power is minus 1. So the plus 1 and the minus 1 cancels out, and I have p squared plus this summation p choose j, p to the power p minus j minus 1 to the power j, j equals from 0 to p minus 2. Now if you look closer, you would realize that each of these terms have at least each term have at least p cubed in it, right? So each term is divisible by p cubed. And the reason is simple, because simply when you look at it, these terms, each of these terms will have at least a p squared in it, and each of these will contribute at least one more p, right? For instance, this binomial coefficients, p choose j, is simply equal to p factorial j factorial p minus j factorial. None of these would divide the p, right? So the p will remain intact. So they will cancel out with the remaining terms, but not the p. So this will contribute at least one p. So in total there will be 3 p cube here, but then only a single p squared here, suggesting that this whole expression here is divisible by p squared, but not p cubed. So therefore, so therefore finally we can say that our expression p raised to the power p minus 1, because this expression has a p squared in it and a bunch of other terms, so this divides a p squared and then a term a, so so this would simply imply that p raised to the power p minus 1 divides p squared, So therefore, knowing that P is an odd prime, this would imply that P is simply equal to 3. And we already established earlier that N was simply equal to P from here. So therefore, N is also equal to 3. And that's the final solution. So we have the following solution. So therefore, to conclude, the solutions have the following form. 1P, where P any prime. We established 2 works. And finally, we established that 3 also solves this problem. Now, notice that we have made use of this fact, the second condition here of the problem, only once. It turns out that this is a redundant condition. However, it simplifies the problem greatly in establishing that N must be equal to P. If this condition is dropped, the solution will still be the same, except that the question would become significantly harder. It can no longer be a number 4 in an IMO, but rather it would be a number 5 or even a number 6 in an actual IMO. So therefore, so yeah, that solves the problem, and we are done.